Errors almost always indicate blockage of the pitot tube, the static ports, or both. Blockage may be caused by moisture, including ice, dirt, or even insects. A blocked pitot tube affects the accuracy of the ASI, but a blockage of the static port not only affects the ASI, but also causes errors in the altimeter and VSI. If the pitot tube becomes blocked and its associated drain hole remains clear, RAM air is no longer able to enter the pitot system. Air already in the system vents through the drain hole, and the remaining pressure drops to ambient outside air pressure. Under these circumstances, the ASI reading decreases to 0 as shown above, because the ASI senses no difference between RAM and static air pressure. The apparent loss of airspeed is not usually instantaneous, but happens very quickly. If both the pitot tube opening and the drain hole should become clogged simultaneously, then the pressure in the pitot tube is trapped. No change is noted on the airspeed indication should the airspeed increase or decrease. If the static port is unblocked and the aircraft should change altitude, then a change is noted on the ASI. The change is not related to a change in airspeed, but a change in static pressure. Because airspeed indications rely upon both static and dynamic pressure together, the blockage of either of these systems affects the ASI reading. Remember that the ASI has a diaphragm in which dynamic air pressure is entered. Behind this diaphragm is a reference pressure called static pressure that comes from the static ports. The diaphragm pressurizes against this static pressure and as a result changes the airspeed indication via levers and indicators as seen above. The pitot tube may become blocked during flight due to visible moisture. Some aircraft may be equipped with pitot heat for flight in visible moisture. Consult the AFM POH for specific procedures regarding the use of pitot heat. If the static system becomes blocked, but the pitot tube remains clear, the ASI continues to operate. However, it is inaccurate. If the aircraft descends, the static pressure increases on the pitot side, showing an increase on the ASI. This assumes that the aircraft does not actually increase its speed. The increase in static pressure on the pitot side is equivalent to an increase in dynamic pressure, since the pressure cannot change on the static side. If an aircraft begins to climb after a static port becomes blocked, the airspeed begins to show a decrease as the aircraft continues to climb. This is due to the decrease in static pressure on the pitot side, while the pressure on the static side is held constant. Shown above, a blockage of the static system also affects the altimeter and VSI. Trapped static pressure causes the altimeter to freeze at the altitude where the blockage occurred. In the case of the VSI, a blocked static system produces a continuous 0 indication. Some aircraft are equipped with an alternate static source in the flight deck. Flight deck static pressure is lower than outside static pressure. Check the aircraft AOM POH for airspeed corrections when utilizing alternate static pressure. Advances in digital displays and solid-state electronic components have been introduced into the flight decks of general aviation (GA) aircraft. In addition to the improvement in system reliability, which increases overall safety, electronic flight displays (EFD) have decreased the overall cost of equipping aircraft with state-of-the-art instrumentation. The multi-panel digital flight displays combine all flight instruments onto a single screen, which is called a primary flight display, or PFD. The traditional 6-pack of instruments is now displayed on one liquid crystal display, LCD screen. Configured similarly to traditional panel layouts, the ASI is located on the left side of the screen and is displayed as a vertical speed tape. As the aircraft increases in speed, the larger numbers descend from the top of the tape. Airspeed markings for VX, VY, and rotation speed, VR, are displayed for pilot reference. As on traditional analog ASIs, the electronic airspeed tape displays the color-coded ranges for the flap operating range, normal range, and caution range. One improvement over analog instrumentation is the larger attitude indicator on EFD. The artificial horizon spans the entire width of the PFD. This expanded instrumentation offers better reference through all phases of flight and all flight maneuvers. The attitude indicator receives its information from the Attitude Heading and Reference System, AHRS. The altimeter is located on the right side of the PFD. As the altitude increases, the larger numbers descend from the top of the display tape, with the current altitude being displayed in the black box in the center of the display tape. The altitude is displayed in increments of 20 feet. The VSI is displayed to the right of the altimeter tape and can take the form of an arced indicator or a vertical speed tape. Both are equipped with a vertical speed bug. The heading indicator is located below the artificial horizon and is normally modeled after a horizontal situation indicator, HSI. As in the case of the attitude indicator, the heading indicator receives its information from the magnetometer, which feeds information to the AHRS unit and then out to the PFD. The turn indicator takes a slightly different form than the traditional instrumentation. A sliding bar moves left and right below the triangle to indicate deflection from coordinated flight. Reference for coordinated flight comes from accelerometers contained in the AHRS unit. The slip skid indicator is the horizontal line below the roll pointer. Like a ball in a turn and slip indicator, a bar width off-center is equal to one ball width displacement. The turn rate indicator is typically found directly above the rotating compass card. Tick marks to the left and right of the lubber line denote the turn, standard rate versus half-standard rate. Typically denoted by a trend line, if the trend vector is extended to the second tick mark, the aircraft is in a standard rate turn. The sixth instrument normally associated with the six-pack package is the tachometer. This is the only instrument that is not located on the PFD. The tachometer is normally located on the multifunction display, MFD. In the event of a display screen failure, it is displayed on the remaining screen with the PFD flight instrumentation. Individual panel displays are able to be configured for a variety of aircraft simply by installing different software packages. Manufacturers are also able to upgrade existing instrument displays in a similar manner, eliminating the need to replace individual gauges in order to upgrade. Electronic flight displays utilize the same type of instrument inputs as traditional analog gauges. However, the processing system is different. The pitot-static inputs are received by an air data computer, ADC. The ADC computes the difference between the total pressure and the static pressure and generates the information necessary to display the airspeed on the PFD. Outside air temperatures are also monitored and introduced into various components within the system, as well as being displayed on the PFD screen. As shown on the right, the ADC is a separate solid-state device which, in addition to providing data to the PFD, is capable of providing data to the autopilot control system. Trend vectors are magenta lines which move up and down both the ASI and the altimeter. The ADC computes the rate of change and displays the 6-second projection of where the aircraft will be. Pilots can utilize the trend vectors to better control the aircraft's attitude. By including the trend vectors in the instrument scan, pilots are able to precisely control airspeed and altitude. Several flight instruments utilize the properties of a gyroscope for their operation. The most common instruments containing gyroscopes are the turn coordinator, heading indicator, and the attitude indicator. To understand how these instruments operate requires knowledge of the instrument power systems, gyroscopic principles, and the operating principles of each instrument. Two important design characteristics of an instrument gyro are great weight for its size, or high density, and rotation at high speed with low friction bearings. There are two general types of mountings. The type used depends on which property of the gyro is utilized. A freely or universally mounted gyroscope is free to rotate in any direction about its center of gravity. Such a wheel is said to have 3 planes of freedom. Restricted or semi-rigidly mounted gyroscopes are those mounted so that one of the planes of freedom is held fixed in relation to the base. There are 2 fundamental properties of gyroscopic action. rigidity in space, and precession. Rigidity in space refers to the principle that a gyroscope remains in a fixed position in the plane in which it is spinning. An example of rigidity in space is that of a bicycle wheel. As the bicycle wheels increase speed, they become more and more stable in their plane of rotation. This is why a bicycle is very unstable and very maneuverable at low speeds, and very stable and less maneuverable at higher speeds. Precession is the tilting or turning of a gyro in response to a deflective force. The reaction to this force does not occur at the point at which it was applied. Rather, it occurs at a point that is 90 degrees later in the direction of rotation. This principle allows the gyro to determine a rate of turn by sensing the amount of pressure created by a change in direction. Using the example of the bicycle, precession acts on the wheels in order to allow the bicycle to turn. While riding at normal speed, it is not necessary to turn the handlebars in the direction of the desired turn. A rider simply leans in the direction that he or she wishes to go. Since the wheels are rotating in a clockwise direction when viewed from the right side of the bicycle, if a rider leans to the left, a force is applied to the top of the wheel to the left. The force actually acts 90 degrees in the direction of rotation, which has the effect of applying a force to the front of the tire, causing the bicycle to move to the left. There is a need to turn the handlebars at low speeds because of the instability of the slowly turning gyros, and also to increase the rate of turn. Precession can also create some minor errors in some instruments. Precession can cause a freely spinning gyro to become displaced from its intended plane of rotation through bearing friction, etc. Certain instruments may require corrective realignment during flight, such as the heading indicator. In some aircraft, all the gyros are vacuum, pressure, or electrically operated. In other aircraft, vacuum or pressure systems provide the power for the heading and attitude indicators, while the electrical system provides the power for the turn coordinator. Most aircraft have at least two sources of power to ensure at least one source of bank information is available if one power source fails. The vacuum or pressure system spins the gyro by drawing a stream of air against the rotor vanes to spin the rotor at high speed, much like the operation of a water wheel or turbine. A typical vacuum system consists of an engine-driven vacuum pump, relief valve, air filter, gauge, and tubing necessary to complete the connections. The gauge is mounted in the aircraft's instrument panel and indicates the amount of pressure in the system. Vacuum is measured in inches of mercury less than ambient pressure. As shown above, air is drawn into the vacuum system by the engine-driven vacuum pump. It first goes through a filter, which prevents foreign matter from entering the vacuum or pressure system. The air then moves through the attitude and heading indicators, where it causes the gyros to spin. A relief valve prevents the vacuum pressure or suction from exceeding prescribed limits. After that, the air is expelled overboard or used in other systems, such as for inflating pneumatic de-icing boots. It is important to monitor vacuum pressure during flight because the attitude and heading indicators may not provide reliable information when suction pressure is low. Aircraft use two types of turn indicators, turn and slip indicator and turn coordinator. Both instruments indicate turn direction and quality, coordination, and also serve as a backup source of bank information in the event an attitude indicator fails. Coordination is achieved by referring to the inclinometer, which consists of a liquid-filled curved tube with a ball inside. The gyro in the turn and slip indicator rotates in the vertical plane, corresponding to the aircraft's longitudinal axis. A single gimbal limits the planes in which the gyro can tilt, and a spring tries to return it to center. Because of precession, a yawing force causes the gyro to tilt left or right, as viewed from the pilot's seat. The turn and slip indicator uses a pointer, called the turn needle, to show the direction and rate of turn. The gimbal in the turn coordinator is canted. Therefore, its gyro can sense both rate of roll and rate of turn. When rolling into or out of a turn, the miniature aircraft banks in the direction the aircraft is rolled. A rapid roll rate, causes the miniature aircraft to bank more steeply than a slow roll rate. The turn coordinator can be used to establish and maintain a standard rate turn by aligning the wing of the miniature aircraft with the turn index. The above image shows a picture of a turn coordinator. There are two marks on each side, left and right, of the face of the instrument. The first mark is used to reference a wing's level 0 rate of turn. The second mark on the left and right sides of the instrument serve to indicate a standard rate turn. A standard rate turn is defined as a turn rate of 3 degrees per second. The turn coordinator indicates only the rate and direction of turn. It does not display a specific angle of bank. The inclinometer is used to depict aircraft yaw, which is the side-to-side movement of the aircraft's nose. During coordinated straight and level flight, the force of gravity causes the ball to rest in the lowest part of the tube, centered between the reference lines. Coordinated flight is maintained by keeping the ball centered. If the ball is not centered, it can be centered by using the rudder. To center the ball, apply rudder pressure on the side to which the ball is deflected. Use the simple rule, step on the ball, to remember which rudder pedal to press. If aileron and rudder are coordinated during a turn, the ball remains centered in the tube. If aerodynamic forces are unbalanced, the ball moves away from the center of the tube. As shown above, in a slip, the rate of turn is too slow for the angle of bank, and the ball moves to the inside of the turn. In a skid, the rate of turn is too great for the angle of bank, and the ball moves to the outside of the turn. One additional tool which may be added to the aircraft is a yaw string. A yaw string is simply a string or piece of yarn attached to the center of the windscreen. When in coordinated flight, the string trails straight back over the top of the windscreen. When the aircraft is either slipping or skidding, the yaw string moves to the right or left, depending on the direction of slip or skid. During the pre-flight, check to see that the inclinometer is full of fluid and has no air bubbles. The ball should also be resting at its lowest point. When taxiing, the turn coordinator should indicate a turn in the correct direction while the ball moves opposite the direction of turn. The attitude indicator, with its miniature aircraft and horizon bar, displays a picture of the attitude of the aircraft. The relationship of the miniature aircraft to the horizon bar is the same as the relationship of the real aircraft to the actual horizon. The instrument gives an instantaneous indication of even the smallest changes in attitude. The gyro in the attitude indicator is mounted in a horizontal plane and depends upon rigidity and space for its operation. The horizon bar represents the true horizon. This bar is fixed to the gyro and remains in a horizontal plane as the aircraft is pitched or banked about its lateral or longitudinal axis, indicating the attitude of the aircraft relative to the true horizon. The gyro spins in the horizontal plane and resists deflection of the rotational path. Since the gyro relies on rigidity and space, the aircraft actually rotates around the spinning gyro. An adjustment knob is provided with which the pilot may move the miniature aircraft up or down to align the miniature aircraft with the horizon bar to suit the pilot's line of vision. Normally, the miniature aircraft is adjusted so that the wings overlap the horizon bar when the aircraft is in straight and level cruising flight. Every pilot should be able to interpret the banking scale illustrated above. Most banking scale indicators on the top of the instrument move in the same direction from that in which the aircraft is actually banked. The relationship of the miniature aircraft to the horizon bar should be used for an indication of the direction of bank. The attitude indicator is reliable and the most realistic flight instrument on the instrument panel. Its indications are very close approximations of the actual attitude of the aircraft. We hope you learned a lot. Please help us spread the word about Pilot Training System, and we look forward to further servicing your flight training needs.